Hello, everybody. Welcome to Rational Science.
Hey, guys.
Got my son today with me. We're going to argue, fight, wait for questions, whatever. And today we're delivering the Gettysburg Address. Did I say Gettysburg? The State of the Union Address. No, that's not either. No, it's the State of Physics Address.
State of Physics.
The State of Physics. Is physics in a deplorable state or what? Okay, so we're going to talk a little bit about the state of physics, and then we'll open the floor for questions. People want to have some questions, real time. If we can answer them, we'll answer them today. Otherwise, we'll take it as homework and give you a rain check. Okay, how's that? Okay, so let's get started here. Where do we start? I mean, if we're going to give you the State of Physics Address, I guess it'd be nice to do a little history, a quick history of, where we started and how we ended up here, okay? And so let's start over here. I'm going to start with the Greeks, okay, very quickly. And these were the fellows who were involved with physics and mathematics. They started with geometry and so on, and these people, we inherited our stuff from them primarily, but, there were the Babylonians and the Egyptians even before them. And they also argued the same questions that we argue today. We haven't solved them in 2,500 years. We have not solved them. They asked, is there motion? And started putting words like infinity into the record. They talked about infinity quite a bit. And I guess the fellow who was probably the closest to my way of thinking, at least for that age, I mean, we're talking about 2,500 or more years ago, was Democritus. He said, he had a famous saying, allegedly attributed to him, saying, all there is atoms and empty space. The rest is mere opinion.
Hey, you got pretty close.
Now, he got pretty close. The only thing I would add to that is atoms, empty space, and the ropes connecting all atoms in the universe. Yep. That would be the only change I would make, okay? But yeah, these were the schools, okay? And this lasted for many years. There was no real revolution until the 17th century. We had other people in between who did things, had theories and so on, but a lot of them were religious oriented, traditional religions. That was one issue. The other issue is they did not really develop mathematics to a great level. And above all, as we will see in the 17th century, they did not do experiments. That was a no-no. That was a sin. Okay? You would go to hell if you didn't do an experiment. And that's what the people in the 17th century essentially introduced. Here's a group of them, okay, around the, primarily in Europe, right?
They didn't do the experiments, or they did do experiments?
They did not.
They did not.
You mean up to the 17th century, it was like, it was just intuitive, okay. It's like, I know that. It's like, I don't need to test it.
Yeah.
That's what changed, essentially. People had these ideas, and they never tested them. That was one of the criticisms that the 17th century changed. Okay, and so you have these again. These are not the only folk. These are just the some of the most important names. Let's see if I can get this.
You want me to do it?
There we go. I had to make it bigger. Okay, anyways, the 17th century introduced specifically experiments. Okay, a lot of these people started doing experiments, measuring and developing math to higher levels. And one fellow who put it in the right context, he essentially synthesized it for what science became after that, was Galileo. And he said the following. It's important to read what he said. Philosophy is written in that great book which ever is before our eyes. I mean, the universe. But we cannot understand it if we do not first learn the language and grasp the symbols in which it is written. The book is written in what? Mathematical language. Mathematics is the language in which God has written the universe, meaning physics, right? And he added there, I think that in the discussion of natural problems, we ought to begin not with scriptures, but with experiments and demonstrations. So this more or less synthesized what the revolution was about. And all these people that I mentioned, they did experiments, they did measurements, and they started changing, the way we think about what's out there. Not only the universe, the solar system primarily, but things like vacuum. You had Torricelli, you had, who was it? Fellow by the name of Gede also in Germany. And they did experiments on vacuum, for example. Another one was Robert Boyle. He did experiments on vacuum. So much so that Charles II, who had just come back to England, said, I'm paying this guy to do what? To study air. That's the way you put it, more or less. What are these guys doing? Studying air? Vacuum?
Do you think they put such a heavy point on experimenting all of a sudden because there were fallacies? Like people just believed things that just weren't true, and then it's like, well, what? It's like they're trying to get some stable foundation. Like, what is reality? Let's make sure that things do fall to the ground. Let's make sure. Is it like a double checking of what we believe?
I think what happened was even before the 17th century, there were people who were criticizing Aristotle. Until then, Aristotle was the law, right? And whatever he wrote, everybody just read, memorized, and kept going. More or less like today. We read all this other stuff from quantum mechanics. We just memorize it, right? And just repeat it. That's what they were doing all throughout the Middle Ages, you could say. And what happened was, you reached like the 17th century, the 16th century, people like Simon Steven in Holland, and he decided to test Aristotle's claim that, heavier objects fall faster than lighter ones. And he went to a tower over there in, I think it was Amsterdam, and he dropped these two rocks on wooden planks out the bottom. And he said they hit at the same time. So he dropped a heavy one, a lighter one, and he did the test. He did it when Galileo was still in shorts. He was playing hooky from school.
That's the thing. They started finding more and more assumptions were off.
Right.
So they're like, okay, what is real?
Well, that was one issue. The other issue with people like William Gilbert, he tested magnets because he wanted to know, what kind of magic this thing was, why it has these magical properties. So he played around with magnets more or less like Faraday would do, a couple hundred years later. But, they started questioning and they started changing the way of thinking of people. And there was a lot of communication between the mainland Europe and England and, Italy, France, Germany. These countries had all these people who were doing research, testing some of their own theories, their own, their way of thinking, and they started changing some of these things. Another one was that you have to remember that's when Protestantism, got away from Catholicism, and that's an important background here because the new kings, the new princes who took over, especially the northern part of Europe, they wanted a separation from Rome. And here were these scientists who were saying, what Rome is saying is not absolutely true. We can't go by scriptures, as Galileo said. We have to, science is different, and that's something.
They like that. They like the politics.
That was also in the background, like, hey, let's break with tradition, with religion. We don't do religion in science. Let's, keep it, let's keep that, what belongs to Caesar, what belongs to God, that kind of thing, so that was also in the background. Anyways, things more or less remained like that until maybe the 19th century. The only changes there were when they came up with a wave nature of light, which was Robert Hooke, 1665 in his Micrographia.
1665, you already had the wave?
Yeah. He came up with a wave. He was looking through the microscope. He saw this halo, and he started saying, hey, light has wave properties. Then Huygens mathematized that. But he did it for longitudinal waves. And it wasn't until, the Thomas Young that brought up at the break of the 19th century, brought up the fact that, that maybe it's a transverse wave. And he wasn't the only one. There were a couple French guys even before them that were already shooting that possibility.
Transverse is up and down?
Transverse is up and down and forward.
Okay.
Whereas the other one is the waves like, sideways and, in one direction only. Whereas this one is up and down.
Yeah.
Okay. So like water has a little components of both, but they didn't really zero in on the transverse wave until Fresnel, in, France, was able to explain, the polarization with that. That's when really they started picking up on the wave nature of light. And throughout the 19th century, it was all wave nature, with the ether serving as the backdrop, as the thing that moved. And that was kind of overthrown towards the end of the 19th century when Michelson and Morley did their experiment and showed that, there is no ether, or at least that was a conclusion of most mathematicians. And that lasted until the beginning of the 20th century. The 20th century, we had another revolution, and that's the quantum/general relativity revolution. That's what we have today. And, maybe, because that's changing too, okay? So, here we get to the, people in the 20th century, okay? And these are some of the heroes, that you read about in the literature. All these people, there's a lot more, obviously, but these are some of the big names of the 20th century that, developed something. Either they did experiments that were, groundbreaking, and they also did the theory, right? They theorized and came up with new ideas. Okay, but what were those ideas? The ideas were the ones that we live with today, essentially, to a great extent. And who do we have today? What is the 21st century? What kind of people do we have here? Who are the heroes of today? Well, here we are. These are the heroes that carry the torches today, right? And as you can see, I haven't called them theorists or physicists. I call them celebrities. Yeah. Because that's exactly what they are. They are nothing but celebrities. People who study, memorize. I don't call it study. I call it memorizing. They memorize at the university and develop skills on how to do mathematics. And then they're hired as
mouthpieces.
As mouthpieces, that they deliver the message to the masses, and they claim to know. And in the same breath, they claim not to know. They say, we don't know anything, but we know everything. So we have that situation today, that duality.
Is the difference with the people nowadays that they haven't added anything, or
yeah, that's
are they just spouting what
you hit it right on the nose? That's one of the issues. The issue is we haven't had anything. In fact, we're going to get into that in a second here, but they haven't added anything in the last 40, 50, 60 years. They're really, since the days of quantum, 1926, thereabouts, there hasn't been really anything new except just more particles, and they study more particles, but there's really no new theory underlying, the atom or, the universe. We still have space-time, and we still have the, Bohr's atom.
Well,
the little bead going around the nucleus. That hasn't changed.
Some people would say that. I mean, even you would say that when you get the answer right, then it doesn't have to change anymore. But they would. But it's not that they got it right. It's just.
Well, let me tell you, they don't have it right. I'll tell you why they don't have it right. On the relativity side, we have space-time. Space-time is just number lines. It's not dimensions, it's not coordinates, it's not vectors. It's number lines. These are just numbers. And they say that gravity is the warping of time, of one of the number lines, called time. It makes no sense. That's not a physical interpretation. And so everybody is studying out there, how the universe works, and nobody can tell you, why this falls to the floor. Very simple. I just want to know why this falls to the floor. And they're talking about black holes, dark matter, and who knows what else. And so, yeah, in that sense, we still have space-time. And in the quantum world, we still have the same atom. Nobody can draw the atom because whatever they draw, the little ball with the little the nucleus, meaning the proton ball in the center, and the electron bead going around, that's the planetary model. And I don't care if you use the exact model that Bohr suggested, which is an orbit. The model today is that the electron can be anywhere, jumps around, and it can be anywhere. Or, but worse yet, it's everywhere. It is everywhere at the same time because it's a wave, or they turn it into a wave.
It's a cloud of potentiality.
Yeah, because they put it at their convenience. They use whatever model they need to use to explain something. That's the problem. So, they constantly move the goalpost. The point here is that, that we have all these particles. What are we going to do? Just keep smashing particles to find out what particles they're made out of, for the next million years? And so, again, they right now we're what is known as a crisis. There's a crisis in physics. And I'm going to let a couple people here talk for me. Here's Sean Carroll, okay? Listen to him. He'll tell it to you in his own words.
In fundamental physics, we've not had any breakthroughs that have been verified experimentally for a very long time. That's just true. Can't argue with that.
What if the past 40 years of fundamental physics research have been leading us down a dead end? What if there's something historically and structurally rotten that's holding us back from understanding the true nature of reality?
Yeah, what's holding us back is mathematical physics. So that's what's structurally and historically wrong with what's going on with physics. We have to get rid of mathematical physics because mathematical physics hasn't answered a single question in the last 2,500 years. We still have the same questions that the Greeks had, and we haven't answered them with all the technology and all the theories that have been thrown over the years. Here's another fellow. His name is Roger Penrose, and he has this to say. He says, conclusions is not what collapses the wave function. He's talking about the wave function. You have a wave, suddenly it collapses to a dot.
Consciousness.
Yeah. Collapses. Consciousness. I'm sorry. Consciousness is not what collapses the wave function. In other words, you have the wave, and it collapses to a point. That's when you can measure. Right?
Well, that's because they say that when you look at it, that's when it...
But that's what he says. Yeah. He says, so there's something in physics which collapses the wave function. The Schrodinger equation, quantum theory as a whole, is wrong. Now, this is a guy who just won a Nobel Prize 2 years ago. He's telling you, after 100 years, right, that quantum is wrong. The Schrodinger equation is wrong. Quantum mechanics is wrong, okay? Einstein and Schrodinger said it was incomplete. Okay, incomplete means wrong.
Yeah, I mean, yeah.
So, and this is, again, I want you to note that this is a Nobel Prize winner, right? A very important guy. He was a right-hand man, I guess, or at the same level as Stephen Hawking. And you can see what he's saying. He's saying, after all these years, they're telling us quantum is wrong. And why did we study quantum at the university? And finally, here we have another another lady, and her name is Sabine Hossenfelder, German lady, and she does
Science is Failing, Still the Same Crap.
Yeah.
What kind of titles are these?
Yeah, the crisis in physics is real. Science is failing. She says, still the same crap. This is why physics is dying. And she says, I get very depressed that nothing has changed in 20 years. Well, really, this is...
I think you have to send her an email.
No.
Hey, lady.
No, something's wrong. And this is what's wrong here. Let me show you what's wrong. She's depressed because she's going to the bank every day, depositing her money. She's making a lot of money acting as a contrary person, as a challenger, when she is not. She believes in quantum mechanics. She believes in relativity for the most part. Einstein's her hero. So why is she acting as a challenger? Who is she challenging? Who is she fighting against then? Isn't that the status quo, relativity in quantum mechanics?
Do you think that it a little bit of that has to do with the fact that there aren't even debates? You don't hear any open debates of physicists,
because the debates are between people who think the same way. So it doesn't matter if they all think the same way. They're just running around in circles. It's not like these people are bringing someone new that has a different opinion than all of them.
Yeah.
And the system is already evolved to that point where you can't publish a paper unless you first say, quantum is correct and relativity is correct. You
gotta bow to the right gods.
Yeah, you gotta bow to the gods. And if you don't do that, you don't get your paper published because the peer reviewers, the secret peer reviewers, immediately will throw your paper in the trash can. If you happen to say, I think Einstein was wrong. That's it. That's the first set.
How dare you?
Yeah.
It's like Jesus
so
and Christianity.
all we have is they're hearing their same voices. There's a bunch of echoes. That's all we have, And so all these people are really not scientists. What they are is celebrities. They're making money just peddling the same stuff we had for the last 100 years. That's it. That's all we have.
I think that's why everyone's bored of physics.
Yeah. Here are a set of questions that I just came up with out of the top of my head. Okay, just one right after another. Can they answer any of these questions? Is the universe infinite or finite? Can anybody tell me that for a fact? After 2,500 years, because the Greeks were asking these same questions. What is space? What is space? They say space is a physical object. Okay, please draw it. I want to see what space looks like. If it's an object. What is a singularity? We have two versions. We have the singularity version where you are falling into the rabbit hole, but never make it there. Okay, it's
whatever that means.
Yeah, you're falling, never make it there. And the other one is that it is a dot, a zero-dimensional dot. And both of those are nonsense, poppycock. Dark matter, they have no idea what it is. And I can tell you right now what it is. It's a variable in an equation. That's all it is. That's what dark matter is. They put a variable there. They say, now our equation is correct. And they tell the astronomers, go look for it.
This is the go look for it part. They're like, it's invisible, go look for it. What?
Yeah. And dark energy. What is dark energy? Well, they don't know what energy is, let alone dark energy. Maybe have yellow energy, white energy, But they don't know what energy is. They never defined a word. And Richard Feynman said, we have no idea what energy is. Yeah, but everybody uses the word. Oh, yeah. It's like we don't know what a spirit is, but
we like using it.
But it's the spirit that moved the curtain.
It helps us talk.
What's a mediator of gravity look like? Is there a mediator for gravity? Is there one for light? What does an atom look like? Nobody can draw an atom. Whatever they draw, they say that's not it. That's not the real atom. Yeah. And so I never seen an atom drawn. Nobody can draw. Show me, where the electron is, where the proton is.
Like a cell. Like you think they could draw an atom like a cell. A cell you can draw. This is the fucking nucleus of it. This is the border of it. Right. This is this part, the mitochondria.
And I don't care what the real atom looks like. I don't care about that. I want to know the atom that the researcher, the theorist that's going to give a theory, I want him to tell me what his atom looks like that I can tear it to pieces.
I've never seen a cell, but if someone drew it for me, I could understand what they're talking about when they're talking about it. Maybe this is the mitochondria. They look like this.
Right.
But with an atom, they show me a ball going on a ball. I'm like, well, what keeps that ball to that ball?
Yeah.
No, well, it's not actually like that.
Because you want to make sense. You want to make sense of what you're seeing on the screen. The guy talks in the background, you see on the screen, you're done. But when they can't put anything on the screen, and you say, "Listen to me, let me tell you, with the how we explain our math."
The gravity one.
They're not explaining physics; they're explaining the math. That's what they do when they talk about explanations. What keeps the electron bound to the nucleus? Why doesn't it fly away?
What keeps the moon to the earth?
What separates one universe from another? Here you have, let's see if I can see it here. Where is it? Well, I'll show it to you in a minute. We have the multiverse, right? Many universes. What separates one universe from another? If the multi-universe is a valid theory. So if the guy comes in, gives you a presentation, says, I'm going to talk about the multiverse today. Okay, tell me what separates one universe from another. Very simple. If you can't identify that thing that separates two universes, because every universe is self-contained. It's got space, time, matter, Jesus Christ, God, the whole thing. Then what separates that universe from another universe?
They're in different realities. That's what it is.
Yeah, but I just need to know the separator, the medium that separates them. What is that?
The reality separator, obviously.
By what mechanism does a virtual particle come into existence and then disappears? Give me the mechanism. I want to know.
Talking about
don't just say that, what they do, they bring the magic wand and they say abracadabra, and the virtual particle comes in, the equation comes out right, they say, hey, we're done. We did our work for the day, because they put in an ad hoc factor in there. Which quickly goes away because they say we can't detect it in the lab, but our equations are now correct. And again, they tell the guy at the lab, say, go look for it, for the virtual particle. And they say, we tried, but it keeps going
it's
back.
virtually there.
I call them magical particles. That's what they are, magical particles. Do fields go through each other? You have these fields. You have the magnetic field. You have the electric field. You have the muon field, the pion field. All these fields are out there, right? They're all superimposed. Do they go through each other? Because people say, hey, Bill, how can a rope go through another rope? Well, how can a field go through another field if a field is, vibration of a field is a particle? If that's what they're accelerating in these accelerators, and we can see the bang, in the bubble chamber, then the question is, what did they accelerate? Did they accelerate a peninsula, all along the field? So we have a problem there. Can a particle be at two locations?
That's the best one.
Yeah, I mean, if that doesn't ring a bell, then you're not qualified to do physics.
And just to clarify every time, it's not one particle becoming two, it's one particle in two places at the same time.
Yeah. And then how does gluon keep quarks together, okay? We have these gluons, and they pull two quarks together, but they're supposedly particles that jump back and forth. So I throw the rock at you, how do I pull on you? That's the only thing that quantum mechanics and general relativity, for that matter, have never been able to explain. Attraction, pull. The force of push is easy. With particles, it's easy. I throw the ball at you, push you away, we're done. How do you pull? By throwing particles. And again, that shows
negative.
Yeah, that's what they do. It's a mathematical trick.
It's a negative push.
So we have this. This is their conclusion, essentially. That mathematical physics preaches that objects in QM and GR, right, general relativity, behave in weird and unusual manners.
And do they?
Here you have some examples. These are just a few examples. There are length contraction, particles at two places, time travel to the past, kill your grandfather. Tachyon so fast, faster than light, it arrives from the future. Abstract singularity attracts objects. You have the singularity of a black hole. It influences a star far away. How does it do it? How does this little singularity do it? Mass is a concept. Numbers known as fields vibrate. You have the field. It's a bunch of numbers, a bunch of values, and they're vibrating. Say the excited field. What do you mean the excited field? All the numbers get excited or what?
Calm down, field. Calm down.
Spinning Earth drags time around, proven by gravity probe B. I mean, what is all this? Is this science? Is this a state of physics? Right?
Next time I go to work and I come late, I'm going to tell them I dragged time around.
Yeah.
I was dragging time, boss.
What time was dragging you on you?
Time was dragging on me.
Mathematical physicists urge you to believe that quantum relativity are idiosyncratic. They behave very special in a very special way.
Well, one thing I want to say to all this is this isn't superficial stuff. This is if you dig just a little bit under the surface, which no layman does.
Right.
No layman ever asks a follow-up question.
Yeah.
No one ever.
Because they think that they don't know enough math to ask the question. But these are not issues of math.
They also don't want to look stupid. Like, I don't even know if I'm asking the right question.
Yeah, right.
They're so out of their depth, and it's like mathematical physicists have taken everyone's like confidence away in a way, because no one even wants to ask questions. They're like, this is so far out. It's like a doctor trying to explain specific parts of a cancer cell to someone. Like, look, you got to go to the university to understand this shit. So why am I even going to ask these questions? Yeah,
but I don't think I have to go to the university to understand why there's only two things, this and the Earth. Why this falls to Earth. I don't need to go to university. It's not an issue of math. It's not an issue of, it's an issue of figuring out, what comes in contact with the skin of the thing that I'm dropping. That's all it is. Anyways, the point is, because of all these weird behaviors, they say it's idiosyncratic. And
I love that word.
I prefer to say that it's idiocy. Just, quantum and relativity are just idiocy. They have nothing at all to do with reality. They're not mapping reality. They have, none of this has anything to do with reality, with physics. Hopefully, if we started doing physics was to understand reality. And that doesn't mean to develop, devices, technology. It has to do with, just thinking, understanding how this universe works. That's all we're talking about. That's what science is about. And you can see where the problems are. Here's the definition of physics from the IOP, Institute of Physics, one of the bastions of physics in the world, and this is what they say. They say, physicists study how the universe behaves and apply the knowledge to improve our lives.
They apply the knowledge?
Absolutely not for both. No and no. If physicists study the universe, right, or phenomena, we're all physicists. We have 8 billion physicists on the planet. So now you can safely say that Bill Gates has given you your degree in physics because we're all physicists. If you just open a book and study the book, you just study, you're a physicist.
Some people would say, yeah.
Yeah, so everybody's a physicist that just studies, that opens a book and says, okay, I read the first page. You're a physicist now.
I mean,
so
I might agree with that. I mean, if you're studying it, you're trying to get to the bottom of it.
But that's why it's a irrational definition, because if a physicist is someone who studies, then, or for that matter, an anthropologist, a biologist, are those people just people who study?
I mean, kind of. Let me give you a different one, a doctor.
Okay.
Like if you're just learning about a specific illness, isn't that a part of doctorhood? Aren't you in that moment kind of a doctor?
Well, yeah, but what I'm saying is we can't define branches of science by saying it's the study of. Everybody studies. Even a kindergartner studies something. They might even have a rudimentary or introductory level of anatomy or physics or whatever. So what? He's suddenly a physicist because he opened a book?
I'd call him a low-level physicist. Yeah, that's what I'd call him. I'd have to disagree with you. I think he's a low-level physicist.
So, I'm saying that, physics has to be defined a lot better than the study of. That's one issue.
What I didn't like is the second part.
Yeah, the second part.
To improve our lives. Yeah, I never had a physicist improve my life.
Let me put this up there. You got to put it up there again.
I've never had.
Yeah, it says, in fact, you see the importance of physics. You'll see there. It says, understanding how the universe works gives us tremendous power to what? Change our world. Yeah, that's not what physics is about. Physics is not about changing anything. It's just about understanding. Many of the biggest changes in our lives have been made possible by physics. Mobile phones, the internet, blah, blah, blah. That's technology. That's not physics. That's not science. That's technology. And these people... This is the Institute of Physics. They don't know what physics is.
Well, they're trying to take the credit. They're trying to big up themselves. Be like, look how important physicists are. Look how important we are.
Yeah, but
if it weren't for us, you wouldn't have phones. You wouldn't have nuclear fission.
Yeah, and that's a notion a lot of people have. That thanks to the physicists, we have even nuclear weapons, which is not true at all. Okay, you have Iran. They have also mathematicians. They don't have the bomb. Yet, at least, as far as we know. So, I mean, technology is one thing, science is another. Okay, so the fact that you study math doesn't mean that you know how to build a bomb, for example. And all they did was discover that from an atom you can get a big bang. That's all they did, which is theory, right? But that doesn't mean that did not translate directly into the bomb. The bomb had to be developed by people who use their hands, not their brains. They went out there, they tried one thing, tried another until they finally built the bomb. But we have this notion that all these inventions required the physicists. And that's absolutely not true. Technology develops by trial and error. You try one thing and you try another. Even today, with all the technology we have the chips, for example. Not a single person working in the chip industry, not a single mathematician on earth can tell you what a magnetic field is. That's the issue. That's the proof that's the only proof that you need that we can develop technology without understanding.
Well, it's like we talked about the other, usually
or different levels
when we talk about these things, it becomes a matter of layers where they can explain it down to a certain layer, down to the layer that's useful, but it doesn't keep going to the nitty gritty of, how does this?
Yeah, but still,
you don't have to know how the electron is pulled to the photon to the proton to be able to use an atom, for example.
But see, one of the things you'll note is that first comes the lab. Before you measure, you cannot create a standard. And before you create a standard, you cannot use that information to build on top of that. In other words, how did we come up with all these values for example, the Gaussian magnetism or the charge on the electron, all this? First, we went to the lab. That's how we did it. We went to the lab first. We measured. Then and then you go to the do some armchair physics and think, and you say, let's see, maybe we'll put a value there, and then we'll test that again, and so on down the line. But the issue is that all of math came from measurement. What is measurement? Lab. So the lab was
that's
the first
why they think
point.
Experiments are so important.
Right, but experiments you can use a magnet without understanding what a field is, and that's the case today. None of these people know what a magnetic field is, but everybody can use a magnet. So does that make you a scientist because you can use the technology, or you can build up a magnet? You know that if you rub a magnet, or some metal with a magnet, you can create a magnetic force there. Yeah, you know that because that's technology, but you don't know what a magnetic field is or how it does it. That's the issue. And so we don't have explanations. We don't have understanding. And those are two different things. Understanding is science. Technology is something else. Developing by trial and error. Anyways, so let's summarize here. What's the state of general relativity? That's the macro world. This is it. We can see it in a single picture here. This is what we know or don't, okay? Almost the entire universe is dark energy. We have 23% dark matter. Then we have a small percentage, 3.6%, which is non-luminous matter. Like black holes, non-luminous. and then the rest is luminous matter, like stars. So you can see that they use that number like saying either it's 96 or so percent or more, really like 99%, really, if you include the non-luminous matter. They say that's a measure of their ignorance. And I say it's true, really. They're very ignorant people. But unfortunately, the public considers these people very knowledgeable, that they're at the forefront of knowledge, of science, when they're really very ignorant people. They know nothing about our universe. They know nothing about reality. They're the wrong people to tell you how this universe works. All they can do is tell you, mathematize it. They can measure and give you an equation, but they cannot tell you how it works, what reality is. And people go to them and they say, tell me what reality is. Why does a spoon fall to the floor? What is light? And they can't.
It gets funnier when the philosophers try to reference what the physicist said.
Right, on top of
then it just gets really weird. When I'm listening to a philosophical debate and they're like, well, they say that an atom is mostly space, and that's why spirits. I'm like, bro.
Yeah.
This is so much.
Anyways, one of the ideas they came up with is the multiverse. We have all these universes, and the funny part, this is a surrealistic image because you can see the stars in the background. So all these universes, each one has time, matter, space, everything inside it. What's separating one universe from another?
What universe are all the universes in?
Yeah, that's the one with the stars in the background. Okay, so this is the version from general relativity.
God's filing cabinet.
But we also have, just in case, the quantum version, here it is. It's like, every step you take, you branch off into different universe.
Oh my God.
Okay, and here you have Schrodinger's cat, he's both dead and alive. In this universe, he's alive, and the other one, he's dead, and so on. And you have the Earth, branching off into different Earths for every step you take. These are the notions these people have out there, and that's what they're developing math for. You might say, well, they don't really believe in this. Yes, they do, because they're publishing this stuff. This is in the literature. Tachyons are in the literature, faster than light, even though Einstein showed through special relativity, and everybody accepts that nothing can travel faster than light, even light. But they had to invent the tachyon because they have to give you hope that somehow you're gonna reach the nearest star someday. So.
What it sounds like is they already got all the rules of the game, and then they just started breaking the rules of the game. at some point. But he didn't know everything. We do have the tachyons, for example.
Here's the quantum version, okay? Quick simile of what the many worlds theory of quantum mechanics looks like, okay? This guy is everywhere at once. He's sitting down, but he branches off into different universes. He does all these things, but each one in a different universe. Like this, sounds like the spirit to me of old. Remember the old religions? They used to have these spirits, and this is what we have today. So, is this physics or what is this? Is this just Hollywood nonsense?
Yeah.
You know, what's it got to do with physics? What's it got to do with science? This multiverse and many worlds and so on.
Well, I mean, just to interject just a bit, Hollywood has given everyone the notion that if you can imagine it, then it could be real.
Yeah, I know. This is unfortunate also because people have lost track of reality. They have their feet off the ground and nobody's touching the ground anymore, you know. This is the quantum atom even to this day, okay, and this is it, folks. You know, the question is, why doesn't the electron fly away? You know, what keeps it bound to, you know, these energy levels or orbitals? Why doesn't it fall to the nucleus? You know? And look at the nucleus. It's made out of, in this case, it's a proton, so you have 2 up quarks and 1 down quark, right? And this is what it looks like up close, okay? And they always put this circle around it. You know, what is this circle? They put it by hand. I mean, what is that circle? How can you put a circle around a triangle? You know, so they put this circle by hand. They say, yeah, that's the proton. When the proton is really 3 quarks, and then the quarks are being pulled together by what? By bed springs? What the hell is that? You know, if you look at the standard model, which is the one they developed over an entire century, you don't find the glue on there. Let me put it over here, see? I mean, you find the glue on, but you find the glue on, but you find it on the upper corner here, and a right-hand corner, and but it doesn't look like a bed spring. It looks like a ball to me. In fact, they all look like balls. Okay, so where did they get this notion that it's a bed spring?
Well, but it's inside the proton. They can't see that far, Bucks.
Yeah, but the point here is that they do these things. They make an image of something, but they cannot explain it. When they explain it, and you call their bluff, and they say, "Look, are you saying that the gluon is a bed spring that?" You know, just pulls in. That's how the quarks are pulled together. They had to do that because if they put particles, people are going to say, "Hold it! It sends particle. How does it attract the quark?" Yeah. Very easy. We put a bed spring, you know, and now
but the bed spring thing is it's a good window into the fact that even they know, everyone knows that there's some mechanics. The quantum mechanics. What does that mean? That means there's some physical mechanism. Like when everyone sees the bed springs, they're like, "Oh, I understand now," because that looks like something that they can picture.
Right.
But then they go, "But it's not actually that."
Right.
Once you dig a bit, they're like,
it's just an analogy.
It's just an analogy. It's like,
but it's a wrong analogy.
It's the same thing with gravity when they do the bed sheet and put the thing.
Yeah,
because everyone can picture that. That is mechanics right there. But then they go, "But it's not actually that."
Right, because if the analogy serves for the theory, then no problem. Yeah. But the analogy has nothing to do with the theory. In other words, they say, look, it's a bending of space-time. And you say, but how do you bend space-time? Well, it's just an analogy. Don't take it so seriously. You know, it's that's the best way we can put our math into qualitative language, into normal language. Bring it down to your level, in other words. They belittle you and they say, bring it down to your level.
Yeah. On top of that, they make you feel stupid. Like, really? You really thought I meant what I said? Yes, motherfucker.
Okay, so here we have the other issue that plagues and why quantum mechanics is dying. Quantum mechanics is being taken over by these field theories. They call it quantum field theory. What do we mean by that? We mean that it's no longer the particle, the discrete particle, which is what quantum meant. Okay? It is now an island. Instead of an island, it's a peninsula. Why? Because it's part of a field. It's the vibration of a field is what is what a particle is. And so it's no longer an island. It's not a discrete island that flies around. It's part of a field. And so if this is what particles are, it's very different than the particle we had at the beginning of the 20th century, which was a discrete particle. And so, quantum field theory has displaced quantum mechanics, and nobody even noticed. Okay, in fact, one of these guys says it themselves. I got it from him. If quantum mechanics is by, specifically a particle theory, a discrete particle theory, and now they're going to say, well, really, the particle is not discrete. It's part of a field. It's a vibration of a field. Now we're talking about a peninsula, and if that's the case, then what happened to quantum? Where did quantum go? We have a problem. And then the problem there, a second problem, is that the field is just a bunch of numbers. Field is defined as values at each point in space. And now they're saying these values are vibrating, and that turns into a particle that now they can accelerate and crash it against another one. Collision, right?
It sounds like you have a semantic issue.
Yeah. The question is whether I have it or they. Yeah. This is an issue there where you have to establish the language. And they say, well, we can't put our equations into quantitative manner or in normal or everyday language. Then your mathematics is not the language of physics, because we want to know the reality. And that's when they branch off into philosophy, and they say, well, philosophy, they deal with reality. We don't deal with reality. We deal with equations. And that's where the problem is. There's a disconnect, because these people don't know what physics is. They can't define it. They're still saying it's the study of, and if it's the study of, we're all physicists because we all study physics, right? You just got a degree in physics because you read half a page of a book.
I'm not that interested in the categorization of what physics is and isn't. I just want to know how gravity works.
Yeah, and that's what everybody wants to know. And we will
never
know
who's a physicist or isn't, but if you're giving me all this extra stuff that I didn't ask for, then...
So why is what they call fundamental physics in crisis? Well, it's in crisis because fundamental physics refers to general relativity and quantum mechanics. What's overthrown them? String theory. String theory is the attempt to merge both of them, and by doing so, they got rid of both of them. Essentially, what they did is they brought the black hole in. By the way, Einstein never believed in black holes. He didn't believe in Big Bang. He didn't believe in the singularity, aside for the fact that he didn't believe in gravity waves and Big Bang, all that stuff. He didn't vouch for any of that. But aside from that, because whether he believed in or not in it, it's really irrelevant. The point here is that, here we have the attempt to merge general relativity with quantum mechanics.
If general relativity is the big and quantum mechanics is the small, how does a black hole from string theory combine those?
That's the point. The point that all the garbage, all the atoms, right, that fall into a black hole, they say if we can study that at that level, we can figure out gravity at the macro level as well. We can merge the equations, because what they're trying to merge is equations, okay? The equations at the micro level of a particle that's falling into a black hole with the macro world. I mean, we can figure out gravity at the micro level, which they haven't, gravitons or warp space. I mean, we have two mechanisms. We have graviton, we have warp space. You can't merge them, period. We're done. They'll never be able to merge that. But if you twist the rules and say, well, somehow if we can figure out gravity for a particle, maybe we can extrapolate that, generalize it, and get to relativity, to the macro world. But what's the issue? The issue is they replace particles with not really, they replace the particles with rings. That's what they are. These are flat rings, as you can see, and they always show them like this, as two-dimensional, right? Flat rings. And they say, proton, for example, is made of quarks, and all of them are just different vibrations of these strings. And they call them strings. You see there and you say, well, I can understand that's a string. No, that's not a string. They're not talking about strings. They're not talking about hula hoops. They're not talking about rings. What they're talking about is lines. The line of, Euclid's line, that's what they're talking about. One-dimensional. These are one-dimensional. There's no such thing as a one-dimensional anything, but these strings are one-dimensional. What does one-dimensional mean in the religion of mathematical physics? An itinerary. So the line is not a line, not a stick. A line means an itinerary. And what they have is, many locations, and they build these rings with locations. So what you're staring at is a bunch of locations. They call them strings. So you say, okay, I see, it's a string. See, people confuse my theory many times, and they say, oh, Bill, you haven't invented anything. Your rope model, your thread theory, it's just string theory. Absolutely not. Mine is three-dimensional. Theirs is one-dimensional.
We have actual strings. They don't even have
they don't
that.
have string. They have itinerary. So when you look at these vibrating strings, these rings, you're not looking at a thing. First of all, as you can see, they're not one-dimensional because you wouldn't be able to see them if they were one-dimensional. That's the first issue. What you saw just now is at least two-dimensional. But it's not even that. What they're talking about is locations. They're talking about the itinerary of something that traces this ring.
And that waves?
And that's what they're waving. They're waving motion. They're waving motion.
But they're not even waving motion. What they're waving is the bus route.
Yeah,
but
not the bus or the route. It's not a road. It's not a road.
It's not a not the road, but the route.
Right, that's what I'm saying. They're vibrating locations. They've got locations all around.
But that's how I imagine it. Every location is like a bus stop, and they're waving the route. Not the road, not the bus,
but it's the
waving
location.
the route.
Let's make sure it's the location. The bus used to be here. We get rid of the bus. The bus used to be here. Let's get rid of the bus. There's two. So we have the location where the bus was, and now they're going to wave the locations.
Yeah.
And it's two-dimensional, because I guess they call it a one-dimensional line, but who knows? They don't even know what they're talking about anymore. Anyways, this is what they're studying. See, that was the simple part. You say, okay, so they replaced particles with lines, meaning itineraries. Okay, great. No, this is what all the math is going into. This is where all the money is going. This is where your bucks are going into. Okay, here it is.
Crazy.
Okay, holographic universe.
Oh my
okay,
God.
The holographic principle. What is it? A property of string theories and a supposed property of quantum gravity. That's what that's what they're shooting for. That states that this description of a volume of space can be thought of, what? Hold on to your seats here, as encoded on a lower dimensional boundary to the region. In other words, they take the Earth there, which is 3D, they're going to map it, right, onto a flat surface. Okay, so they can make like a hologram of that whole thing. And on the right-hand side, you have the same thing for a black hole. You have the black hole. What is it? You take the surface of a black hole, which is this event horizon, which is a concept, and it's going to map whatever is on the inside of a black hole. And that's what all the efforts of math are going into today. Okay, so just so you know where your money's going, to all these institutions, think
it's a big scam.
Well, they don't think it's a big scam because what they're doing, entertaining themselves at the water cooler, just writing equations. But it's like I say here, and I think I synthesize it well here, okay? This is what they're doing, okay? They're developing equations for leprechauns and unicorns. That's what they're doing. So it used to be, all these other things, wormholes and space-time, but they got bored doing all that. Now they're doing, concept on top of more irrational concept. So they're going inside the black hole, trying to figure out, how to build a hologram out of the thing. And see, and what the language has changed because they're no longer talking about, they never did talk about things, but now it's even more abstract. Now they're saying the information that fell into the black hole is mapped on the surface, meaning the event horizon. So if we can study the event horizon, find out all the information, we'll know a lot about what happened, what's inside the black hole, because that's where it's mapped.
How do you even follow that? How do you even read an article and get through it? Because at some point you just go, I don't understand that. Like, what I don't get, and I think I do get it, the fact that any layman who even tries to read an article just goes, I don't understand this, I'm going to go on to something else.
I think a lot of people do that. They say, well, this is over my head, and
what are we even
all these
talking
people,
about
all
anymore?
these people are so smart. They know all those equations. It must be true. And that's all they say, and they just walk away. You have all these people, visitors, subscribers that go to all these people like Hassenfelder and Sean Carroll and Tyson and so on, and they get a lot of views. What are the people listening to? Garbage. They think they get their shot of, science for the week, and they're not understanding anything. And they say, well, yeah, I guess math is a little different. They can't put it into words for me. No, of course, they don't understand anything. They don't understand it. How can they tell you if they don't understand? I mean, if they can't put it into words, it's because they don't understand it. Otherwise, how are you going to ever put reality into words, if not through words instead of through equations? I mean, you need words to express reality.
Yeah.
Reality has nothing to do with equations. Take Father Universe. What is Father Universe? Every atom in the universe at a location, right? And in the next frame of the movie, right, in what I call the universal movie, every atom moves to a new location, different distance with respect to all others. And in the next frame, they move to another location. So in any frame that you wish to analyze, every atom in the universe is at a distance from all others. That's the universe. That's how simple our universe is. The only thing we're going to add there is that all atoms are physically interconnected by some elongated entity. In our case, we propose the rope. It's got to be connected. If they're not connected, how do you do pull? How do you explain gravity? How do you explain things like entanglement? Or even if we were to use the quantum version, the strong force, the gluon pulling two quarks together. How do you pull two quarks together? Bed springs? What is a bed spring? It's an elongated object. You got to put between two things, two particles.
But
so no matter what, you're going to have put something in there.
the reason they're always winning, though, the reason why they're still the physicists is because we don't have a better alternative. Because anytime any better alternative is even put forth, it gets quenched before it even starts.
Yeah, but why? Because the system is already designed. In other words, it's not that it's deliberate. It's just that that's the way the system evolved. These people who are mathematicians have taken over the guild, and you can't put a new idea in there that goes against the grain. Because, if you're going to go against the establishment, you got a problem already. How are you going to publish? They're not going to let you publish. They want you to go through their system, meaning that you have to already repeat, parrot the catechism that was taught already in school. Meaning you have to believe in quantum mechanics, you have to believe in general relativity. Now they're having a problem because they made no progress in 40 years, right? And so they're saying, well, let's move to string theory. What is string theory? More irrational math that has nothing at all to do with reality. And that's where the next few Nobel Prizes will probably go. So far they had no Nobel Prizes for string theory, in great measure because all these people who are talking about fundamental physics, they're criticizing that the string theorists, the stringers, that they're not doing experiments. And, it's kind of already a revolution in that alone, because remember, 17th century brought the experiment into, evidence, into mathematical physics, meaning science, right? And today they want to take it out because string theories, so far, there's two camps. One camp says we have no experiments, it's just thought, it's just ideas.
That's why people hate it.
Right, and the other group says, well, we're still working on trying to get some kind of experiment.
Trying to figure out what experiment to run.
Right.
Okay, but if it's... I think that's why so many people are still resistant to string theory, is because it's too theoretical and there's no experiment that you can even conceive of to prove it or disprove it.
Not only that, it's that it doesn't resolve, at least the quantum part doesn't solve anything, because the fact that a particle is a vibrating string, assuming it's a string, or assuming it's a little, thread, right? Even assuming that, so what? So it's vibrating. What does that change in anything? So a muon is a vibrating string. A pion is a vibrating string. So what? What does that change in quantum mechanics? And again, we're still waiting for the gravity part. How does a particle attract another particle? Well, that's why they had to go inside the black hole. Since they can't get in there to run a test, experiment, they said, well, maybe from afar we can figure it out, And so they're not going to be doing experiments. And if they don't do experiments, then we've made a big change, because suddenly, whatever they started in the 17th century, which was introduce experiment, verify your theory with some kind of experiment. Now that won't happen anymore. Now it's just going to be pure math, and these guys are just going to run away farther and farther into their rabbit hole.
I have an interesting question.
Nobody will be able to follow them.
Do you think physics as a branch of study, I guess, I know you don't want to put it in those terms, but if it had to be a branch, I'm talking about universities specifically. Physics in universities is treated as a branch of study of like there's chemistry, there's biology, then you have physics.
Yeah.
But chemistry and biology, we've been having, at least they can go into nutrition. You have practical uses, things coming out of it. There's progress. Things are being learned on chemistry, on biology. But since nothing new is coming out of physics, how long, or is there even a time, before people start realizing that it's all crap?
Well, the centers like Hassenfelder and maybe even Penrose, some of these people, they're out there and they're criticizing. There's a rising group of physicists, people who went through the grinding machine, university level, that are now saying, well, so where are we now? They're saying they're in a crisis. A lot of them say, no, it's not a crisis. It's just we went into string theory. Well, that's a crisis.
Yeah, I'm wondering if less and less people will even apply to physics if universities at some point go, what do you guys even do?
Yeah, but the issue here is that unfortunately we have people like Hassenfelder getting in the way. She's part of the establishment, and to say that she's a dissident is a long, it's wrong, and she's not a dissident. Yeah. She's kind of getting in the way of progress, because by putting herself in there, what she's doing is really blocking other people who want to question that.
She's watering down the idea of that there's something new to be said here. She's watering it down by, it's like, you're not adding anything yourself. So
right.
What are you doing here?
What does she propose? Does she propose going back to quantum and general relativity? Because this is what she studied, this is what she believes. So she's in the way, really. We got to get rid of people like that, or like Tyson, and all these people are just in the way because they're showing up as dissidents when they're not dissidents. They're really trying to get back to quantum mechanics and general relativity, while the other guys have left that behind and said, no, we're going to do some weird math, irrelevant math, for unicorns and leprechauns.
They don't put it in those terms.
Yeah, that's what they are. They're spirit. They're doing math on spirits. So what? Who cares about their math? Their math is worthless. All the math being developed in string theory is totally worthless. Can go totally in the trash can. Like the phlogistons.
The what?
Phlogistons? You never heard of that? No. Well, they used to have this particle called the phlogiston. Everybody believed it in until they finally let it die by pocket veto.
They finally put one away. They got rid. That was too dumb.
No, but this is from the 18th century, phlogistons. Anyways, see if we have any questions.
We had one.
Let's see.
I wrote it down here.
Oh, okay.
By Uga. I like the name.
Uga.
Can there be neutron stars under the rope model? I don't know if you've heard that one before.
Yeah.
What's the problem there? Like, what's the issue?
We have to put it in the right context, okay? The first thing is that the rope model says that an electron is a shell, is a membrane, okay, that encapsulates the proton star. So it's a different model than the proton ball and the electron bead, okay? So right now, these people are saying that the bead is being squashed to the proton, right? So when you have a proton and an electron, that is a neutron. Not only have you neutralized the charges, but you have the mass of the neutron. And so far so good. The issue is they packed them all together, right? They say, well, we have this ball of neutrons, right? Because there's no electrons flowing around, no protons going around. And that's what they think is a neutron, which is a star that has not become a black hole because it did not have the mass to become a black hole. So it ended up being a neutron, right? Neutron star. And it, usually it spins and it looks like a beacon and who knows what else. Under the rope model, what you have, you can't squash really the membrane all the way to the proton, because if you do that, all you're doing is, by shrinking, all you're doing is releasing rope. In other words, releasing, rope, essentially, more links, towards the outside. And so all you're doing, if that were to happen, you would be squishing all the electron shells, all the electron membranes, ever more so that all the extra rope comes out of that object, okay? And so you would have a dense object, of a massive object full of
a big knot.
Yeah, a big knot, essentially, but they could merge, because I would think that if you can create an atom here on Earth where you can merge one electron shell with another, I can imagine under great pressure out there in a neutron star, you would squish all this so much that, you could conceivably, build this object there called a neutron star. I have doubts about that process. Okay, neutron stars, like so many other things, like the fact that the redshift, has been completely misconceived. I have my doubts still on the neutron, on really what's going on with those stars. You have to look at the process, and we need maybe more brain power to look at these things under the new model. If you have the rope model, how would you explain something like that under the rope model?
That's something interesting that I was thinking of when they said incomplete theory is wrong theory. The funny thing is, I would say the rope model is also incomplete, but not in the parts that count. Right. Like you can explain the foundations. Yeah, you can explain magnetism, gravity, light. Maybe there's some fringe things that we haven't thought of.
Yeah, and again, we need more brain power, more people to simulate whatever these people do in the labs, but instead of simulating them with particles, simulate them with with a rope model. And that's what's happening. That's what should be happening. But we need more brain power.
As a follow-up question to that, if neutron stars do exist and are explained by the rope hypothesis, do they have gravity, and how?
Well, yeah, assuming let's just assume that you squashed all these electron shells together, and release the ropes outwards. So you make this small object that is very heavy, assuming that's the case, okay? And so the question is, would
it have gravity?
Oh, yeah, well, the gravity is the gravitational collapse. And obviously, you have all these atoms squashed, because even though they're neutrons now, we're saying that we've collapsed the electron shell together with a proton star. But what is the solution under the rope model? The neutron simply says that the rope, the thread that goes around and makes the electron shell, has now simply become a rope. So all you have is ropes in there. And so the question is, can we have a star just of crisscrossings of ropes? So would it have gravity? Yeah, because you still have the ropes coming out. Okay, that gravity it would have. The question is, what does it look like inside? That's where we need to put our brain power, inside this object. If such an object exists, maybe there's another explanation for the neutron star. And again, all I can say is we need more brain power, more people coming in and looking at it under a different model of, particle instead of the particle model. We need a change. But certainly not string theory. What are they going to tell you? That's an itinerary that's vibrating? What the hell?
I had someone else asking about ferromagnetic materials, but there wasn't really a question attached. Can you answer my questions about ferromagnetic materials? But I'm guessing it has to do with magnetism.
Well, yeah, I mean, the main thing, I guess you said it just a minute ago. We can answer the main questions, the basic question. How does a magnet attract another? What is light? What is gravity? We can answer these questions with a rope model, with something that you can see and that makes sense and that is in line also with the equations. So we don't need quantum mechanics and general relativity, all this nonsense that they created, or string theory for that matter. We can explain, the simple things, the basic things. Now, people say, well, what about this specific situation? What about this other one? Well, we have to look at it. Some of these are sophisticated experiments. Some of them are not. Some are simple, but it's the question of analyzing them under the rope model. And, it takes a lot of brain power. You need a lot of people to put their brains together and say, okay, this is you take this project, you take this one, like they do today. I mean, everybody doesn't work on everything. This guy works on string theory. This guy works on, general relativity. The other guy works on quantum. We need the same thing, but under the rope model.
And we got the question from Frank Roger here. How are certain materials attracted by magnets and others are not? They are not magnetic in the sense of being magnets because they have no poles and they do not attract themselves, unlike magnets. So he's saying it's not a magnet itself, but it's attracted by magnets. How does that happen?
Well, yeah, one other question is, you put a magnet to your finger and it doesn't attract it. And you say, well, why doesn't it attract my finger? It attracts. And again, all I can say is, we got to look at the structure of the molecules, right? And for this, we need to understand first what ionization is. Ionization, we've all been taught in school that it's a little ball, which is the proton, and you have an electron. We'll do it with a hydrogen atom, which is very simple. We have a proton ball, right, and the electron bead. And the electron bead leaves, and you have a positive, whatever that means, positive ball, right? And when it comes back, or when another one is added, then it's a negative ion, meaning now it's got more negative charge, whatever that is, right, than it had before. And so, we need to look at this under the rope model. Under the rope model, if you want to produce attraction between two atoms, like to form a molecule, through ionization, like ionic bond, well, then you have to have something swinging around in the opposite direction, or really in the same direction as the other guy over here. So they're both swinging like this. One comes down, the other one comes up. What's swinging? The threads that make up the atom. There's a thread being swung around. One thread comes down, the other thread comes up. If you have several of these threads, right, and the other one has several of these threads, now you have this wall of threads that are pulling these two atoms together. So we have a physical mechanism that has nothing to do with this ionization that they talk about, where the bead flies away for no reason whatsoever. And when it comes back, it increases the negativity, whatever that is, so it's just math. What they talk about is just math. They don't have a physical system.
Yeah, but that's a good question. I never thought about asking the fact that some objects, maybe they are magnetic, but at such a low level that, because they're saying things that are pulled by magnets, for example, like a piece of iron, it isn't magnetic itself. It doesn't pull other pieces of iron, but it is pulled by a magnet. And there you can't say that it's the swinging threads because it isn't swinging any threads, or it's just not so much that it's pulling.
No. Hold it. You do have the swinging of threads. Okay, even in a piece of iron, there is the swinging of threads, but you don't have them. They're not excited to the point where they're not going at great speeds or very far away. That's one issue. The other one is they're all swinging in the same direction. Remember, a metal such as iron, right, has all their atoms aligned in the same direction in general, right? It's the structure, the molecular structure of this is very organized. Now imagine a bunch of threads from a magnet, right? Separate from that, right? A separate object. You have this magnet now going through that region, and you have all these metal atoms that are swinging their threads around. Now you can create that situation where they're all going in the same direction. When these come up, these come down, and there's an attraction.
Like they catch the wave.
Right, because they're all pointing in the same direction. But if you take an amorphous materials such as carbon, and they're all going in different direction, the threads of a magnet come through it, but it can't attract it because they're not all going in the same direction. If they're all aligned and going in the same direction, like in the case of magnets, they're known as domains. Well, in a sense, a metal such as iron, They have all the threads swinging the same direction,
but then,
because it's an alignment issue. And when you put a magnet close to them, the threads of the magnet are swinging around. It makes contact with that organization, with that organized piece of metal.
We've gone long, but let me ask the last question then. If you have two pieces of iron that both have that, why don't they attract each other then?
Because again, it's just locally. In other words, it's not excited. You can magnetize a piece of iron. Why? Because when you rub it or you put it to some electromagnetic influence, then what it does, it forces those atoms to swing at a higher speed.
It's excited enough that it gets affected by magnets, but not so excited that it acts as a magnet. That's the weird. Right. That's a weird gray zone.
Because in order to do that, you need to stimulate the atoms to such a point that they're swinging at a greater speed and release the threads farther out. Then you have a magnet. Yeah. But as long as the threads are swing around, because all these atoms are swinging their threads around anyways, but you need to get those threads to come out to a great distance, then you have a magnet.
Okay.
Okay, folks. Well, we'll see you next week, hopefully.
Yep. Okay. There were questions you didn't answer here.
Answer
them in the next one.
I'll take it as homework. You take it as a